Good morning. Today we are going to talk about Prim's algorithm. Here's a video that gives you a brief introduction about the algorithm. First of all, we're going to start about defining a minimum spanning tree. Here we are giving a number of houses in and a number of roads n minus 1. We have to connect each house with other houses with the minimum cost for building the roads as possible. So the image on the left is the minimum total edge weight, which is referred to as a minimum spanning tree, while the one on the right is not. There's another kind of graphs, like directed, undirected graphs, and connected and weighted graphs. Directed graphs have directions on its arrows, while undirected connected graphs are all connected together, while weighted graphs have a weight between each vertex and another one. The greedy algorithm is just like a greedy man, who just chooses the obvious and immediate benefit in front of him. In this example, the man is choosing $12 over 4 and 8, so he can achieve a locally optimal solution, and by applying this, he can lead to a globally optimal one. So, Prim's algorithm is using the greedy strategy to find the minimum spanning tree of undirected graph with the weighted edges, and the graph should be connected, of course, which is faster, especially in dense graph. So, let's have a look on the algorithm itself. Here is a pseudocode for Prim's algorithm. Let's explain this code while examining the analysis and time efficiency of this code. Here, we are using a binary heap as our priority queue. First, we start with the initialization. But before solving the problem, we go through all the vertices of the graph, and setting a key value to infinity, and y to nil. Then, we go to the root, and setting a key to 0. That's different from the keys of all the other vertices other than the root in the graph. Then, we build our heap in a priority queue, which have a copy of all the graph vertices. Both this step and previous for loop is executed in time big O V. As you are trying to find the minimum spanning tree for this problem and the problem is not solving yet, the spanning tree value will be equal to 5 and will always remain with value less than v minus 1. Here, line 6, we say while q is not equal to 5, in other words, number of edges is less than v minus 1, we do extract the minimum of the given q. And for each vertex belongs to the adjacent of extracted minimum in a big O v minus 1, we check if this vertex belongs to setted q and the cost of it is less than the key, which initialized with phi at the beginning, and get updated to make sure we choose the minimum path to this edge. Otherwise we choose another edge nearest to the selected vertex with a lower cost. So the overall time complexity is going to be equal the initialization time plus the main loop time and key update time. So the initialization time is equaling a big OV plus another big OV of building a heap, and execute time V get multiplied to a log V for extracting the minimum, and the key updating time, which is E multiplied to log V. So the total time is going to be V log V plus E log V, which is V plus E log V. So which one we're going to choose? Of course, we're going to choose the larger value. In this case, E dominates the value as it's so much larger and bigger than the V. So the total time complexity is equal to EV log V. And here you can find that we reached the same result using the summation. Oh, and there's an important note we have to notice. Here the runtime varies with the data structure used to implement the algorithm. The table below shows that as the priority queue, when it changes from array, binary heap, and Fibonacci heap, it changes the total runtime for it. Now let's help our friend Monster. He don't know how to implement this code in a real life example.
This code is typical to the previous pseudocode, but implemented in Python, with the same information as comments.
So we're going to implement this code in this example. First, we choose the start vertex and select the adjacents. We choose the minimum one. So we've chosen 7. We will do the same here. We choose 5. Do the same. We choose 6 out of 8 and 14. So we have reached here. Nowhere to go as 7 in the visited nodes. So we return and ask the same question. We choose the smallest and not visited here, which is 8. Then we choose 3. We go to 3. Nowhere to go, so we return. Nowhere to go, as visited before, so we return again. We have 9, not visited, so we go to it, so we return to the start, and find that 15 is not visited too. And here's our minimum spanning tree, applying Prim's algorithm, show it in a gray basset color. Here is the advantages, disadvantages, and the application of Prim's algorithm, and our references. Thanks for watching.